Okay, we're going to talk about some experiments to determine rate equations, sort of experiments we do in school, and they are actually there's a required practicals. I think it's required practical 9, I think it is. There's 2 parts to it. Okay, now there's 2 ways of doing these experiments. One is to use a continuous method. Continuous. And the other way is to use which is a clock method. Just to very briefly say what I mean by this is a continuous method is where, for example, you measure the gas produced and you plot the gas produced against time and you draw a graph and you continually monitor the experiment. The clock method would be more like the disappearing cross method, where you don't continually measure the production of a product. You say, right, I'm going to take how long it takes to form a certain amount of that product, e.g. enough sulfur to make the cross disappear. And generally speaking, the clock method is going to be much more efficient and quick than the continuous method. I think it's practical 9a is this continuous method, and practical 9b is the clock method, which I'll do in a different video because it will make this one too long. So let's just look at this continuous method for the time being, right? So the reaction we're going to look at is the reaction between, again, magnesium and hydrochloric acid. And it's pretty easy to measure the rate of follow the reaction there, because you look at the volume of hydrogen gas formed. You make hydrogen gas, okay. So you can use one of 2 apparatus, which you've got here, right? This one would be the sort of expensive one, where you use a gas syringe and you measure, you get your stop clock and you record what volume of hydrogen gas has been produced at certain individual times. This one is the cheapskate method, which is pretty good actually, and it's probably just as good as the gas syringe. And you get an inverted measuring cylinder and you fill it up with water, and then you collect the hydrogen coming up in bubbles like this, and you measure how much hydrogen has been made. Whichever method you do, you are going to end up with a table like this, aren't you? Okay, so I think the way we've done it is to use the hydrochloric acid concentrations of 0.5, 0.7 and 1. It works quite well. I think if you use 2, it's so fast that it's a bit hard to measure the gas, and if you get much below 0.5, then it's a bit, you're there all day waiting for it to react. Okay, so what you do is you do 3 separate experiments, and it's quite time consuming, because for each one you've got to sit there with your pen and you've got to write down, and you've got to record all of those times, and then you've got to do it for this one, this one, this one, and so forth for the last one. Once you've got all your results, then you have to plot them on a graph. So you get, you might want to do 3 separate graphs, but I'll do them because it gets a bit messy otherwise. So here we've got time, and here you've got volume of H2 collected. I'll just make this axis a bit longer, and you might get something like this. I'm not going to put any units on it. Right, here is, so that's the one at 0.5 mole per decimeter cubed. Okay. Now you can see the rate of reaction slows down with time, doesn't it? And that's because the acid is becoming more dilute. What have we got to do? We have got to measure the rate of reaction, 0.5 mole per decimeter cubed, at time 0. We've got to measure the initial rate. How do we do that? Well, we plot we draw a tangent at time 0 in a different color. And then you put in your construction lines, and you measure the rate. So you measure the volume of hydrogen you produced in a certain time, and you work out your gradient. So initial rate is going to be equal to the gradient at time 0. And then you're going to do it for the 1 molar, right? The 1 molar, it should be a steeper curve. Let's do that, right? So And if you do your experiment correctly, should level out at the same point because you're using the same. You usually have the acid in excess and you have the same mass of magnesium each time. And then finally you can do, so that's the one, that's the points, that's the one, sorry, the 1 mole per decimeter cubed. And then you can do the 0.75 moles per decimeter cubed, which would be less shallow still, yeah. Okay, and for each of those you'd have to plot, so 3, that's why I say do it on 3 separate graphs, because otherwise it's a bit confusing. You've got 3 gradients at times 0. So from your graphs, then you've got to do a bit more processing, so it's all quite time consuming, and you have got to, you end up with a chart like this. You'll have a hydrogen ion concentration, which is the same as the acid concentration, is equal to 1 mole of HCl gives you 1 mole of H plus in mole per decimeter cubed. And you're going to have your rate of reaction, and that rate, it should always really should be measured in changing concentrations of the acid, but we're probably just going to put volume H2 per second. Okay, so you're going to end up, you've got there, you have 0.5, 0.75 and 1. And now you hopefully should have enough data. You've only got 3 data points, and it's taken a long time to do that because you've got to do 3 separate experiments and plot 3 graphs and collect all that numbers. So it takes quite a long time. We've only got 3 data points, but hopefully we should be able to work out which first, second, or third order, or 0 order. Right, let's do the most obvious way of doing it. I suppose what we could do is you can compare 0.5 to 1. Okay, so 0.5 to 1, hydrogen ion concentration has doubled. So if it's first order, the rate should have, from those experiments, should have increased by a factor of 2. If it's second order, the rate should have increased by a factor of 2 squared, 4. That might be enough to determine it, but if not, and to support it, you can now compare 0.5 to 0.75. So what have we done to H plus concentration there? We've multiplied that by 1.5. So if it's first order, the rate should have gone up by a factor of 1.5. If it's second order, the rate should have gone up by a factor of 1.5 squared, which is about 2.25. And finally, if you really wanted to, I suppose you could do a final comparison of 0.75 up to 1. I'll do that over here. So 0.75 to 1, the H plus concentration is increased by a factor of 1.33 recurring. So if it's first order, it should have gone up by 1.333, and if it's second, 1.333 squared, which is equal to 1.77 recurring, I think. Okay, anyway, you get the idea, and you get a good idea of what order that reaction is. It's a fairly not that accurate experiment. It's quite fiddly, and you can see with the trying to start the reaction and not let any of the gas escape. That's all quite. You've got to be on the ball recording the results and so forth. But if you do this, you probably find out that the reaction is certainly not first order with respect to H plus. It's more than that. It's more like second order. Okay, I think it is a second order reaction. In the next video, then we'll do this is the continuous method, which is time consuming. We only end up with 3 data points. Usually you'd want to use a clock method. It's a much more efficient way of doing it. You can end up with maybe 5 or 6 data points, even more. You can plot them on a line and get line best fit and get a much more accurate idea of what's actually going on. Okay, so we'll do that in the next video.